Okay, good morning to all. Today we are going to start real analysis. So in this part we are going to discuss about the real number systems and then properties of real number system. Okay, fully we are focusing on real numbers. Okay, so what are the properties it have? So we know addition property and then multiplication property, right? So we denote R is set of real numbers, set of all real numbers. Now, so what is the algebra of a real number system? That is, what is the addition of two real numbers? What are the properties the addition satisfied, and then what are the property multiplication of real number satisfied? Now we discovered here. So the first one is suppose if we take two real numbers, we know that sum of two real numbers x plus y same as y plus x. Any two real numbers satisfy this condition. And second, associative property, that is x plus y plus z is same as x plus y plus z. For any three real numbers satisfy this. And then identity element, and we know that 0 is the identity element, that is x plus 0 equal to 0 plus x equal to x for all x in R, and 0 is the additive identity. And then the fourth property is inverse, that is x minus or x plus of minus x equal to minus x plus x equal to 0 for all x in R. This minus x is called additive inverse of x. And these are all properties of addition of real numbers. Now, properties of multiplication of real numbers. So the first property, again, if we take any two real numbers, is always satisfy the commutative property, that is x dot y equal to y into x. For any two real numbers, satisfy the multiplicative property. Multiplication with commutative property with respect to multiplication. And then second is associative property, that is x into y dot z equal to x dot y, x into y into z. We take any three real numbers, satisfy this associative property. And then the third property is identity element. So the identity element is nothing but 1. So x dot 1 equal to x equal to 1 dot x. Okay. For any real numbers, satisfy this. So this 1 is called multiplicative identity of R. Okay. Then fourth one is multiplicative inverse. So that is x dot 1 by that is actually we take 1 by x for provided x non-zero. So 1 by x into x we get 1. This is true for any non-zero real numbers. X in R, but x should be non-zero. X in real number, but x should be non-zero. So these are all properties of multiplication of real numbers. So this four property, and this four property for properties of addition of real numbers. Now there is a relation between this addition and multiplication, that is distributive laws is satisfied. Any three real numbers is satisfy the property x dot y plus z. This is nothing but x plus x into y plus x into z. This is actually we called a left distribution law. If you take a right means, if you take x plus y dot z equal to x dot z plus y dot z. So this satisfied any three real numbers. This is actually distributive laws. So these two are called distributive laws. So this is right distributive law, and then this is left distributive law. Okay. So this is a relation between addition and multiplication. Okay. And then the one more important relation in R is order relation. So order relation is if you take any three real numbers, or if you take any two real numbers, the one of them must be true. It's very important property. That property is called law of trichotomy. Law of trichotomy. Trichotomy. It's a very important property. So what the property says, what the law says, if you take any two real numbers, then one of them must be true. That is, if you take any two real numbers x and y, either x equal to y or x should be less than y or y should be less than x. If we take any two real numbers, one of them must be true. Okay, if you take any two real numbers, if you take any two real numbers x comma y in R, either x equal to y or x strictly less than y or y strictly less than x. It's a very important property, law of trichotomy. Okay, now what is the meaning of, so the same notation we can write like this, x greater than y. Okay, using less than or greater than, we can equally write it. Okay, then what is the meaning of this x less than or equal to y? What does that mean? This means that either x is strictly less than y or x equal to y. Either one of them must be true. So that is, we use the notation x less than or equal to y. Okay. Suppose is satisfied both the relation. Suppose they are real number. Suppose if we take two real numbers satisfied x less than or equal to y and y less than or equal to x, then that two real numbers should be equal. Suppose if we take two real number x and y, real number, suppose x less than or equal to y and y less than or equal to x, implies that x should be equal to y. Two real numbers should be equal. That is another important condition. Suppose two real numbers satisfy these two inequality, then two real numbers should be equal. And then we list some of the order relation. So order relation means what? There is an order. So here less than is the order. Okay. So what are the order relation? What are the properties for order relation? Now we list some of the order relation. Okay. So the first one is, suppose if x less than y, suppose x is less than y and y is less than z, then use the transitive, we get then y x should be less than z. X is strictly less than z. So this is actually, this property is called transitivity. Transitivity property. If x less than y, y less than z, then x should be less than z. This is first property. And second order property, suppose if x less than y, if x less than y and z is any real number where z in R, then if you add z both sides, the inequality then will not change. That is x plus z strictly less than y plus z. And then the third property, if you take any positive real number, that is if x less than y and z is positive, then x should be, x into z is strictly less than y into z. If you multiply a positive number to the inequality does not change. Suppose if you multiply with a negative real number, the inequality will change, right? So that is the thing. So the fourth property, so if x is less than y, then the negative of y should be less than negative of x. If you multiply -1 both sides, the inequality changes. This is another order property. And then the fifth order property is that the square of any real number is always positive. That is, for any x in R, we have the x square always greater than or equal to 0. So in particular, 1 is positive. It's very important. So in particular, because 1 is a real number, 1 square is nothing but 1, therefore 1 is positive. Okay, this is another property. So the next order property, suppose if you take two real number, two positive real number, that is x is positive and y is positive, then the product is always positive. Xy is positive. And the seventh order property, suppose 0 strictly less than x, strictly less than y, then 1 by x, or this 0 is strictly less than 1 by y is smaller than 1 by x. Just you cross multiply or divide by x divided by y, we'll get this one. So this order property is very important. So these are all order property satisfied any two real numbers. Okay. Now we will discuss some examples. Suppose we have a real numbers. So examples, exercise 1. Suppose for any real number satisfy this condition x is strictly less than y, then we have one more real number between x and y, that is called the midpoint. Okay, then we have x is strictly less than the midpoint, x plus y by 2 strictly less than y. Okay, so the point x plus y is called known as the midpoint between x and y. Okay, now the second property is very important. Suppose a real number, if x less than or equal to y plus z for all z positive. For all positive z, this is satisfied. X plus y, x is less than or equal to y plus z for all z greater than or equal to 0, strictly greater than 0, even you can take. Okay, then x should be less than or equal to y. Very important property. So for any z positive, this is happen, then x should be less than or equal to y. Okay, so why this is true? So suppose we want to prove this, suppose we want to prove x less than or equal to y, it is enough to prove that x less than or equal to y plus z for all z positive. Okay, so this is true for all z positive. Then okay, what is the proof of this? So this is true for all number. Okay, anyway, study sequence, we will get another proof. Okay. Now the third problem. Suppose we have two real numbers, positive real numbers satisfied x less than 0 less than x less than y. Then if it square it, then we have the square of two numbers also positive, and then always strictly less than this. And if take the square root, is always positive, then the square root of x is less than square root of y. Okay, so provided square root of x and square root of y exist. Okay, and then one more thing, suppose if x less than y, if and only if x power n is always strictly less than y power n. If you take any natural number, for any natural number, this is true. And then the fourth one is the relation between arithmetic multiplicity and then geometric multiplicity. That is, if you take any real numbers, positive real number, that is for 0 strictly less than x, strictly less than y, then we have the square root of xy. The geometric multiplicity is less than or equal to the arithmetic multiplicity. Geometric mean less than or equal to arithmetic mean. This is true. So these are all important examples, exercise. Okay. Now we define what is upper bound of a set, lower bound of a set. Definition. Suppose we have a non-empty set. So definition for upper bound. Suppose we have a non-empty set. Let A is a subset of R. Some subset of real numbers be non-empty. We have a non-empty subset. We say that a real number alpha is said to be upper bound for A. We say that a real number some alpha is an upper bound. Is an upper bound for A. Upper bound of A if we take any number in A should be less than or equal to alpha. That is, if for each x in A we have x less than or equal to alpha. So every element of A is less than or equal to alpha, then we say such an alpha is called the upper bound for the set A. Geometrically means that all the elements, so in the look at the picture, suppose we have a real line. So we have a, suppose we have a set something. Suppose we can find alpha in R such that every number in A always less. Suppose this is a one set A, so this is A and this also A. Suppose the union of these two sets is A. So if you take any element of A, so this is actually our set A, union of these two parts. Okay. So we say A is bounded above, or this alpha is an upper bound. Then if you take any element, is always less than this element. Such an alpha exists, then we say this alpha is an upper bound for A. So in mathematical notation, we can write using the quantifier for every element x in A such that x should be less than or equal to alpha. So this is a definition for alpha is an upper bound for A. So you can say alpha is an upper bound for A if this is happened. Alpha is an upper bound of A if for every element x in A such that x less than or equal to alpha. Okay, so this is the definition. Similarly, we define lower bound. We say alpha is a lower bound of the set, then every element of A is bigger than alpha. Okay, similarly, we define lower bound. So we say our beta is a lower bound. Lower bound of a set A if we take any element x in A such that it's always bigger than or equal to beta, then this beta is called the lower bound of a set A. Okay. So this lower bound beta may not be a member of the set. Similarly, this alpha upper bound may not be a member of A. Okay. Now, when we say a set is to be bounded set, it is both. It has both upper bound and lower bound. Okay. So before that, we define what is bounded above. When we say a set is to be bounded above, it has an upper bound. So definition for bounded above. Again, a non-empty set. So a non-empty set A is a subset of R is said to be bounded above. Is said to be bounded above. So when we say it's bounded above in R, if there is an upper bound for A, if there exists so if there exists alpha in R which is upper bound, which is an upper bound for A. Upper bound of A. So this upper bound is not unique. So for each set, we have a infinitely many upper bound. So if at least one upper bound exists, then we say the set is bounded above set. So similarly, when we say a set to be bounded below set, there is at least one lower bound exists for the set. Okay. So if we use the quantifier, we can write that there exists a alpha in R such that if we take any element x in A such that x less than or equal to alpha, then we say A is a bounded above. So this is the definition for A is bounded above. So A is bounded above if there is an element alpha in R such that if you take any element x in A, x should be less than or equal to alpha. So this is a quantifier definition of bounded above. So similarly, we define bounded below. Yes, set A is said to be bounded below. A is bounded below if there is at least one lower bound exists. That is, there exists a beta in R such that if you take any element x in A, beta is less than or equal to x. So this bracket is very important. So this means what? Some layer by layer we can write the statement. So why we need this layer by layer definition? We can suppose what do you mean by A is not bounded above. So this is a definition for A is bounded above. So what is the definition of A is not bounded above? When we say A is not bounded above, so A is, you got to take the negation. A is not bounded above. When we say A is not bounded above, it does not have any upper bound. Is not bounded above if you take the negation. So what is the negation of there exist? For every. So for every alpha in R bracket, what is the negation of for every there exists x in A such that what is the negation of greater than or equal to is less than or equal to, it should be greater than or equal to. So if you take any real number, we can always find a real element in R which is bigger than or equal to alpha. So that means what? Alpha is not an upper bound. We can always find another element which is bigger than alpha. Therefore, we cannot find such an alpha. So that's why the writing the statement in the layer by layer, it is very useful to write the negation of the statement. Now, this is the definition for A is bounded below. If there is a B such that this one. So when we say A is not bounded below, A is not bounded below means what? A is not bounded below, then there is no lower bound exist. If what is the negation of for every, there exists for every. So if you take any real number such that what is the negation of for every, there exists a point in A such that what is the negation of this less than or equal to is greater than or equal to, that is beta is greater than or equal to x. So that is there is no lower boundary exist. If you take any real number, we can always find a number from A which is below x. So below beta, that is lower, is not bounded below. So that's why we use the quantifier notation. Now, when we say a set is said to be bounded, if it is both bounded above and then bounded below, then we say it's a bounded set. Okay. So next definition, a set A is said to be bounded if A is both bounded above and then bounded below. Bounded above set and then bounded below set, then we say A is bounded. Bounded below. Okay. Now, if we take some examples, so I already said that the upper bound and the lower bound is need not be a member of the set. Okay. So for example, if we take first example, we take A equal to the open interval 1, 2 is an interval. This is subset of R. Now, what is the upper bound? Upper bound is you can take 2 or 3 or anything more than 2 is always an upper bound, because if you just to draw the picture, so this is 1 and 2, so this is our set A. So when we say a number is said to be upper bound, it should be every element of A is always less than or equal to that number. Suppose you fix alpha here, then every element of A is always less than or equal to alpha, therefore alpha is an upper bound. Or you can take alpha here, this is also an upper bound. If you take alpha here, that also upper bound. Therefore, even you can take these two, because 2 is not included, that is not an issue. Therefore, if you take 2, that also an upper bound, because every element of A is always less than or equal to 2. Therefore, 2 is an upper bound. Or if you take any element more than 2, is always an upper bound. But the upper bound is not a member of A. Since 2 is an upper bound, right? But 2 is not a element of A. So 2 is an one of the upper bound. 2 is an upper bound of A. But 2 is not a member of A because we take open 2. Okay. So therefore upper bound is need not be a member of the set. Similarly lower bound. So 1 is a lower bound but 1 is not a member of the set. 1 is a lower bound of A but 1 is not a member of E. Therefore, the upper bound, lower bound need not be a member of the set. Okay. And then what is the relation between a upper bound and lower bound of the set? Is always, so suppose alpha is an upper bound and beta is a lower bound. So upper bound of A and beta is a lower bound. Of A, then beta should be less than or equal to alpha. Okay, this is simple, right? Because since alpha is an upper bound, that means what every element of A should be less than or equal to alpha. Since beta is a lower bound, therefore everything should be bigger than or equal to beta. Therefore, we get alpha, beta is less than or equal to alpha. Therefore, if we take any bounded set, if the lower bound, upper bound exist, then the lower bound is always less than or equal to upper bound. It's very important. Okay. Now, another important definition. So I already said that once at least one upper bound exists, then the set have a infinitely many upper bound. So among the upper bound, you have to take the least upper bound. That is, we say supremum or least upper bound. So definition for least upper bound. So when we say a real number is a least upper bound of the set, first of all, it's an upper bound and they should be least. So definition, let a non-empty set A of R be bounded above. So for bounded above set only we can talk about the upper bound. Okay, suppose we take bounded above set. This is a guarantee, bounded above guarantee that at least one upper bound exists. So suppose we have some bounded above set. Then we say a real number alpha is said to be least upper bound or supremum. A real number alpha is said to be a least upper bound. A least upper bound are sometimes called supremum or supremum of A. If so, when we say alpha is a least upper bound, first of all, alpha should be an upper bound. So the first condition is alpha is an upper bound. That is the first condition we have to check. Alpha is an upper bound of A. That is the first one. Now second, if we take any other upper bound, then alpha should be less than beta. Because we have to put so that alpha is the least one. Suppose if we take some other upper bound, if beta is an upper bound of A, then alpha should be less than or equal to beta. Okay, sometimes equal. Okay, so this is the definition of least upper bound, or sometimes short we can use the notation LUB. LUB, least upper bound. Okay, or supremum. Now we denote this least upper bound alpha is sometimes use the LUB of the set A, or sometimes use supremum of the set A. Okay. Similarly, we defined infimum or the greatest lower bound. So definition. So a non-empty set, and we are talking about lower bound, therefore should be bounded below set. Okay. So let A is a subset of R be non-empty bounded below set. Be a non-empty bounded below subset. Bounded below subset of R. Then we say a real number beta is said to be greatest lower bound, or alpha, take anything beta. So we say R a real number. So a real number beta in R is said to be greatest lower bound. Greatest lower bound, or sometimes called, in short we use GLB, greatest lower bound, or infimum of a set A if, first of all, that beta should be a lower bound. Beta is a lower bound. Among the lower bound, beta is the greatest. That is the next one. So lower bound of the set A. And if you take some other lower bound, suppose I am taking gamma, if some gamma is a lower bound of A, then what is the relation between this gamma and beta? Beta is the greatest one, therefore gamma is less than or equal to beta. If beta satisfies these two conditions, then we say beta is the greatest lower bound, or we call infimum. So now we denote this beta as greatest lower bound of A, or we can use infimum of the set A. Okay. Again, the infimum or the GLB need not be a member of the set. Similarly, that infimum or the supremum is need not be a member of the set. Okay. Now, if you take any set, it has a unique infimum, unique supremum. Okay, that is very important. So therefore, suppose we have a two least upper bound of a set, then the two numbers should be equal. Okay, so therefore that is a very important thing. Okay, now remark. Suppose if you know alpha is the least upper bound, suppose you are removing something from alpha, then the resulting number is need not be a upper bound. So remark, suppose we have a upper bound. If alpha is a least upper bound, is the least upper bound, because it should be unique. Okay? If alpha is the least upper bound of A, and suppose if we take some positive number epsilon, so epsilon is positive, then if you subtract epsilon from alpha, we call that number is some beta. So beta, I am defining alpha minus epsilon. Then this number is not a upper bound. Is not an upper bound. is not an upper bound of A, because alpha is the least one. Suppose you are subtracting some quantity, some positive quantity, the number is not an upper bound. So this number is not an upper bound means what? Suppose we have a set A, so this is A, and suppose this is alpha. So alpha is the least upper bound. Among the upper bound, alpha is the least one. Suppose I am subtracting some positive quantity, so therefore we get alpha minus some epsilon here. So this number actually beta. So this beta is not an upper bound. So that means what? We can find a element x after this beta. We can find at least one element because it's not an upper bound. Okay, therefore at least we can find one element after this beta. Okay, therefore we have a least upper bound. If you subtract some positive quantity, the resulting number need not be an upper bound. Similarly, suppose we have a lower bound. Suppose you are adding some positive number, then the resulting number is need not be a. Suppose we have some gamma. Suppose we have gamma here. So suppose gamma is the lower bound. Suppose we can add some positive number, we get some gamma plus epsilon. Then this number is need not be a, is not a lower bound. So that means what? We can find some other element here which is below gamma plus epsilon. So that is the meaning of least and then greatest. Okay. Suppose one upper bound is a member of the set, that upper bound should be a least upper bound. So I already said that upper bound need not be a member of the set. Suppose at least one upper bound is a member of the set, that upper bound should be a least upper bound. That is the first remark. Okay, now example or exercise. So suppose if an upper bound alpha is a member of the set, if an upper bound, at least one of the upper bound. So upper bound alpha of A belongs to A. So that means what? Is a member of A, belongs to A, then the LUB of A is nothing but alpha. The LUB of A is nothing but alpha. That's the only possible. Okay. So how to prove this one? The simple proof. Suppose we take LUB some other beta, we have to prove that beta equal to alpha. Okay. So proof. So let we call beta is the LUB of A. But already we know that alpha is an upper bound. It is given and then alpha belongs to A. So by the definition of LUB, every element of A, for every element x in A, x should be less than or equal to beta. We know this. And already is given that alpha is a member of A. Therefore, in particular, alpha is less than or equal to beta. We get one. Okay, now it is given that alpha is an upper bound. Okay, so and we know that beta is the least upper bound. So alpha is an upper bound, beta is the least upper bound. Therefore, what you will know that the least element is always bigger than or equal to that upper bound, because alpha is an upper bound, beta is the least upper bound. Therefore, we get this inequality. Now compare this inequality, we get alpha equal to beta. Therefore, we prove that LUB of A is alpha. So if a set contains one upper bound, that upper bound must be a LUB. Okay. So if you take any open interval, so maybe we'll discuss some examples to find the LUB and then GLB of or infimum or supremum of a set. So exercise. Suppose if we take A equal to open interval 0, 1, open 0, open 1. So actually what is the definition of this? Set of all real numbers lies between 0 and 1, but excluding 0 and 1. All real numbers lies between 0 and 1. So this is the open interval 0, 1. Now, what is the LEB? So clearly the LEB is upper bound is of any number bigger than 1 is an upper bound, any number below 0 is lower bound. So therefore the LEB of A is 1. So first we have to prove this one. So we are guessing that LEB is 1 and then GLB of A is 0. We are guessing this, but we have to prove this. So how to prove this one? So anyway, every element of A is less than 1. Therefore clearly 1 is an upper bound. 1 is an upper bound of A. Because every element of A is less than 1, therefore 1 is an upper bound. Now what we have to prove? We have to prove 1 is the least upper bound. So how to prove 1 is the least? Sorry?
So we can take another upper bound for this set 2 and then 1 is less than 2. So
suppose we have to prove that 1 is the least one. So that means what? Suppose if you are removing some quantity, some positive quantity from 1, that resulting number need not be an upper bound. Otherwise, if you take some other upper bound, we have to prove that suppose I take some, so let B be an upper bound. We take some other upper bound, we have to prove that 1 is smaller than B. Okay, upper bound of A. Okay, now what is that idea? Suppose I am taking B is an upper bound, therefore every element of A smaller than this small b. Now how to prove this one? So we have to prove that what is our claim? We have to prove that 1 is less than or equal to B, because we have to prove that 1 is the smallest one among all the upper bound. 1 is the least one. We have to prove this one. Okay, suppose not, suppose this is not happen, suppose not. So that means what? B is less than 1. This is greater than 1, greater than or equal to 1. Suppose not means what? B should be less than 1. So since B is less than 1, so that means what? B lies in the interval, the set actually. B lies in the interval 0 to 1. Now we can take the midpoint of 1 and B. So suppose B is here. So this is a open to 0, 1. Suppose we want to prove that B should be here. Suppose B is not here, therefore B should be inside the interval. So we can find the midpoint here. So maybe we can call that number is some y. And y is nothing but 1 plus b by 2. Now we have a relation b is less than y. This y is a member of A, which is a contradiction to the b is an upper bound. Upper bound means every element of A is smaller than b, but we can find a element y which is bigger than y. Therefore b should not be inside the interval. Therefore b should be outside the interval, or sometimes b equal to 1. Okay, so if you assume we got to prove that without Laplace generative, we take the so we have to prove that 1 is less than or equal to b. Suppose not, therefore b should be less than 1. That means what? B should be in the interval. Therefore if you mark this is 0 and then this is 1, but b is strictly less than 1, therefore b is somewhere here. Therefore we can take the midpoint. So that is 1 plus b by 2. So this is a number of the set A. Therefore this b is less than 1 plus b by 2, which is a contradiction because b is an upper bound. So that means what? If you take any element x in A, x should be less than or equal to b. But I am taking particular this element 1 plus b by 2, which is bigger than b, which negates, which contradicts this definition of b is an upper bound. Therefore our supposition is wrong. Therefore this is correct. Therefore we prove that 1 is the least upper bound. Got it? Similarly, we have to prove that 0 is the greatest lower bound. So first we have to prove that 0 is the first of all lower bound. Since every element of A is always bigger than 0, right? Therefore 0 is the one of the lower bound. We have to prove that 0 is the greatest lower bound. Suppose if we take some other lower bound, we have to prove that 0 is bigger than this one. So clearly 0 is a lower bound of the set A. We have to prove that 0 is the greatest one. Suppose if we take some other number, so let we take some gamma be another lower of E. Now what we have to prove? To prove gamma is smaller than gamma is less than or equal to 0. We have to prove 0 is the greatest one. Suppose not. Suppose 0 is gamma is not less than or equal to 0. Same thing. Suppose not means what? Gamma should be positive. Here we are saying we have to prove that gamma less than or equal to 0. Suppose not means what? Gamma is positive. Since gamma is positive, therefore gamma should lies in the interval. Right? So same thing we have to take. So this is our interval 0 to 1. See, we already proved that gamma as a 0 is an upper bound. Suppose if it takes, we have to prove that gamma should be here. Suppose not, therefore gamma should be here. Okay. Then what will happen? So some maybe gamma somewhere here also, but that is the worst case. But suppose we take gamma is here, we can find a element here. So what the element we can choose? We can choose that element y. We take the midpoint of these two. So therefore, this gamma we can choose, sorry, the y can be choose minus v by 2, because 0 midpoint of 0 and gamma is minus v by 2. So this is an element of the set A that is open to 0, 1, which is less than gamma, which is a contradiction to the gamma is a lower bound. So gamma is a lower bound means what? Every element of, for every element x in A, gamma is less than or equal to x. But if you take this y is smaller than gamma, therefore gamma cannot be inside the set. Therefore if you take some other lower bound gamma, that gamma should be always below this 0. Therefore 0 is the greatest lower bound. Okay. So therefore if you take any open interval, the lower endpoint is the greatest lower bound, the upper endpoint is a greatest lower bound. If this is an upper bound, this is the least upper bound, this is the greatest lower bound. Even if you take the closed interval, the endpoints also infimum and then supremum. Okay. Any doubt in this? Okay. Now the important property of real numbers, if you take any bounded above set, definitely it has a least upper bound. So the existence of least upper bound. So that property is called LEB axiom. It's very powerful result in real analysis. LEB axiom. So what the LEB axiom says, it guarantees that at least the existence of supremum for a bounded above set. So that is property is called LUB property. LUB, that is least upper bound property of the real number. So this property true only for the real numbers. If you take rational numbers, it will not work. So therefore this property enjoyed only the real numbers. So what is the property? Given any non-empty bounded above set, given any non-empty subset of R which is bounded above, subset of R which is bounded above, which is bounded above in R, there exists a least upper bound. there exists alpha in R such that alpha is the supremum or least upper bound, such that alpha should be LUB of the set A. So what is the LUB property says, if you take any bounded above set, definitely it has a least upper bound, and that least upper bound should be in R, may not be in A. So the existence of LUB guarantee that the LUB property, and there is no proof, there is no direct proof for this property. Actually, that's why we call this a property. But we can prove this using some other, assuming some other statement. Okay, we will discuss later. So similarly, we state GLUB, that is the greatest lower bound, GLB property of the real number R. That is, if you take any bounded below set, it has a greatest lower bound. So given any non-empty, so same thing. Given any non-empty subset of R which is bounded below subset of R which is bounded below, then it has a greatest lower bound. Bounded below in R, then there exists beta, there is a real number, we call some beta in R such that beta is the infimum. That is, beta is greatest lower bound of the set A. Okay, it's a very important property, LEB property. This is a result only true for if you take any subset of R. So it is very important point. If you take any non-empty subset of R, but if you take subset of Q, the result is not true. Okay. So similarly here, this be subset of R is very important. Why this true? If you take subset of rational numbers, even if you take bounded above set, the LEB exists, but it not belongs to Q. So what is the important property of this statement is subset of R is the first one, and then bounded above in R is the second important thing, and the LEB should be in R. So similarly for the lower bound is bounded below is very important, and then subset of R is very important, and then the greatest lower bound should be a member of R. Now, why this result is not true in any other subset? Suppose if we take some subset of Q, the LEB property does not hold. So that is very important example. We take a remark. So remark, suppose we consider some subset of Q and is satisfied all the assumption, that is a bounded above, but it have a least above bound exist, but does not exist in Q. Suppose I am taking the set A is set of all rational numbers such that what is the condition is satisfied? X square is should be less than 2. We are collecting all the rational numbers, satisfy the condition x square is less than 2. Now, clearly this is subset of Q because we are collecting elements from Q. Now, clearly this set is a non-empty set. Why? Clearly 1 is a member of A because 1 square is less than 2. 1 is a rational number. Therefore, 1 is a member of A. Therefore, A is a non-empty set. Okay. Now, we have to prove that next we have to check this is a bounded above set or not. Yeah, clearly since x square is less than 2, therefore x is less than square root of 2. Anyway, every member of A is less than or equal to some number. That number is root 2. Therefore, we have one upper bound, namely root 2. Therefore, A is bounded above set. So A is bounded above. In R. Why? Because root 2 is one of the upper bound. Root 2 is an upper bound. Upper bound of A. Now what we have to prove? This A have a least upper bound, but the least upper bound does not exist from Q. It exists from R. So can you guess what is the least upper bound? So every x is less than or equal to root 2. Actually, the LEB of this one is actually nothing but root 2. Okay, so there is some proof is there. So the LEB of the set A actually root 2. But root 2 is not a member of Q. Therefore, this subset A of Q does not enjoy the property of LEB. So why? Because the LEB says if it takes a subset of R, that LEB should be comes from R. So suppose you are saying that the property holds for Q. If you take any subset of Q, the LEB should be comes from Q. But the LEB is root 2. Root 2 is not a rational number. Okay, therefore, the subset of Q does not enjoy the LEB property or LEB axiom. So LEB axiom true only for a subset of R. Okay. Now, any other doubt? This. Okay. Anyway, so I can stop now. And the next class we discuss about Archimedean property, all other things. Okay. Thank you.